In this tutorial, I'm going to do a demonstration of FM, which stands for Frequency Modulation Synthesis. Now, FM synthesis is most often associated with the Yamaha DX7 classic series of synthesizers, and then they had some other models that in that DX line that also produced FM synthesis. FM synthesis was really kind of discovered or designed by a Stanford researcher named John Chowning, and then he licensed that to Yamaha. Now, we're going to demonstrate this on Thor in Reason, and some of you who know this Thor instrument well will know that there is an FM oscillator that you can add in to Thor. So you can create DX7 type sounds right out of the box using the FM synthesizer or oscillator. Sorry, but we're going to do it a little differently. Rather than using the FM pair, I'm going to show you that you can achieve a similar result, frequency modulation, using an analog synthesizer. If the synthesizer is flexible enough to allow you to route the output of one oscillator into another. So what I'm going to do to get started, I've loaded Thor, and I'm going to reset the device so I can start from scratch. For this particular sound, I want you to know that the sound you're hearing is strictly coming from the oscillators. So I'm going to bypass this filter. And this is what the default sound from that one analog oscillator sounds like. It's kind of a buzzy, sawtooth sound. I'm going to change that to a sine wave. In our discussion in the class before, we've had a definition of FM synthesis. I think you remember the types of synthesis we've discussed are subtractive, where you start with a harmonically rich waveform like a sawtooth or a square wave, and you use a filter to shape the harmonic content of that harmonically rich waveform. There is wavetable synthesis, where you start with a predefined waveform. There was granular synthesis that we looked at, and we've talked about it a long time ago, but I want to remind you how FM synthesis works. Basically, we're going to use nothing but two sine waves. Now, what you may remember about sine waves, this one here, is that a sine wave is a waveform that's kind of thin sounding. And it's thin sounding because it consists primarily of a fundamental pitch with no harmonics above it. So sine waves are often used for, well, a variety of reasons in electronic music. People use them for sub-bass sounds and things like that. But in the audio world, they're sometimes used for hearing tests. Does that remind you of the last hearing test you had? Okay, so again, it's a fundamental pitch with no harmonic content to speak of. All right, what we're going to do is use another sine wave to modulate the frequency, basically the pitch of that oscillator. Now, you've done that many, many, many times before using a low frequency oscillator. And when you apply a low frequency oscillator to a sine wave, it basically produces vibrato. I'm going to set that up really quickly just so you can see what it sounds like. The source will be oscillator 1. Nope, sorry, let me change that. The source will be LFO 1. The destination will be oscillator 1 pitch, and I'll crank up the amount. And you can hear that LFO modulation. Basically sounds like vibrato. Okay, let's undo that. Turn that off. This back down to 0. And I'll turn that off for now. What we're going to do, the reason the LFO produces a vibrato effect is because an LFO, low frequency oscillator, operates in a frequency range that is lower than human hearing. So in other words, it produces waveforms, but it produces them so slowly that we don't perceive them as a pitched sound. right? What we're going to do in this situation, FM synthesis uses an oscillator that's producing a waveform at a much higher frequency rate in the audible range. But rather than routing that output to an amplifier, what we do is we use it to modulate the frequency of the first oscillator. That sounds really confusing. Even confused me when I said it. But just watch the steps, and I think you'll catch on. So again, we're back to just our sine wave sound. I'm going to add a second oscillator, analog oscillator, and also set it to a sine wave. Now, we won't hear it just yet. What you remember about Thor, those of you that have used it, is you got to route that oscillator. Now we should hear it. You'll hear it more if I tune it up an octave. And you can hear the two oscillators sounding. Okay, but I'm going to take this second oscillator and turn it off. It's still producing waveform, and it's still producing a sine wave, but it's not contributing to the sound that we hear. So when I play, we're hearing just oscillator 1. And now, here in the modulation matrix, what I'm going to do is I'm going to take that sine wave, that audio range sine wave, and I'm going to route it to modulate the frequency of this first oscillator. And what it'll do is it'll change the timbre. It creates things called side bands. It creates, basically, to simplify things, it creates harmonic content above that, surrounding that fundamental pitch. So again, this is my source. I'm going to choose oscillator 2, the one that's not turned on. We're not hearing the sound output of that oscillator. That's my source. Destination will be oscillator 1 frequency. And it even reminds you in parentheses there, FM, frequency modulation. So we're going to use the pitch, the sounding pitch of one oscillator to modulate the frequency of the first oscillator. Okay? In FM terminology, this oscillator 1 here would be called the carrier waveform. So imagine just a sine wave that's creating a sound. Oscillator 2 in this scenario is the modulator waveform. So we're not hearing oscillator 2 directly. Instead, it is changing constantly at a very high frequency rate, the frequency or the pitch of oscillator 1. And we won't hear that as vibrato. It's happening so quickly, we won't hear it as vibrato. We'll hear it instead as changing the timbre of the first sound. So again, two oscillators, both sine waves. We're hearing the output of oscillator 1. In my modulation matrix, I have the source, oscillator 2. That's our modulator. The destination, the FM or frequency of oscillator 1. And now I'll play a note over and over and gradually increase this amount. And as I increase the amount, you'll start to hear a change in timbre. Getting very metallic sounding. And the more I increase it, changes the sound more and more. You can do the same thing with negative values. Okay, it'll change the timbre. I'm going to leave this set for now in the 30 range. And I'm going to try some other things to alter the sound. Now let's take the pitch of oscillator 2, which is our modulator, and I'm going to bump it up a couple of octaves. It's really starting to sound kind of bell-like. If I detune this oscillator, maybe take it up a few semitones. Do you hear the harmonics, the side bands moving around? So you can get all sorts of interesting kind of clanging effects. starting to sound kind of like an electric piano, maybe a little bit like a Fender Rhodes. If I increase the sustain, or the release time, sorry, of the envelope generator, I can make it sound more like bells. And again, that's produced with just 2 sine waves on an analog synthesizer. That is just a brief example of FM modulation, frequency modulation, to create sound. It's a type of synthesis. This modulation is not altering a sound, it's actually creating the timbres. Experiment with this. Again, 2 sine waves. Note the routing here. Output of oscillator 2 routing, modulating, the frequency of oscillator 1. And then on Thor, you have these neat chorus effects that really doctor the sound really nicely. That's it for this tutorial.